Tonight, we will follow the oldest light in creation and encounter galaxies still visible, even though their present can never reach us. Then, we will cross 3 cosmic horizons. Beyond the last may lie more universe than humanity can ever observe. This is not merely the limit of our telescopes. It is the edge of cause and effect, the boundary between what can enter our story and what can never touch it. And it is not where or what we imagined. Part 1. A sphere made of time. Stand beneath a dark sky, far from the glow of cities, and the universe appears to surround you. Stars lie in every direction, gathered into the pale river of the Milky Way. Beyond our galaxy are billions of others, receding until even powerful telescopes struggle to separate them from the black. It is tempting to imagine that we are looking outward through space, but in truth, we are looking backward through time. The moon appears as it was a little more than 1 second ago. The sun, roughly 8 minutes ago. The nearest star beyond it, more than 4 years ago. Andromeda appears in light that began its journey about 2.5 million years earlier. Nothing in the sky is shown to us in the present. Every view is delayed. Farther away, the delay becomes immense. We see galaxies as they were before Earth existed, then as small young galaxies assembling the first great structures. Eventually, we reach a limit, not because our telescope is too weak, but because the universe has a finite age. There has only been so much time for information to travel. This limit is the particle horizon. It encloses everything whose signals have had time to reach us. Its present radius is about 46 billion light years. Double that, and the observable universe is roughly 92 billion light years across. And here is the apparent contradiction. If the universe is only 13.8 billion years old, why is its visible radius not 13.8 billion light years? Because while the light was traveling, space itself was changing. Imagine 2 marks on a strip of elastic. Light travels from one towards the other while the strip stretches beneath it. The light never exceeds its own speed, yet the space separating the marks continues to grow. The oldest light reaching Earth began when its source was much closer. During its journey, the universe expanded. The matter that emitted it is now vastly farther away than 13.8 billion light years. This is how a young universe can contain an observable region so enormous. But the particle horizon is not a shell of matter. An observer in Andromeda would have a different sphere centered upon Andromeda. Every distant observer would have their own. Every observer stands at the center of their own observable universe, not because any of them occupies a special place, but because every view is limited by how far information has traveled to reach that particular point. And at the surface of our sphere is the oldest light we can see, a veil hiding almost everything that came before it. Part 2. The first light. Travel backward through the history of the universe, and familiar objects gradually disappear. First, mature galaxies give way to smaller, more chaotic forms. Then, the stars themselves vanish. We enter an age before planets, before suns, before the first galaxy had begun to shine. At last, we meet a glow filling the entire sky. The cosmic microwave background. It is called the universe's baby picture, the moment the cosmic fog became transparent. For roughly the first 380,000 years, the universe was hot, dense, and filled with charged particles. Photons repeatedly scattered from free electrons like headlights in thick fog. As expansion continued, the universe cooled. Electrons joined with atomic nuclei, neutral atoms formed, and the fog lifted. Light was released across the cosmos. That light has been traveling ever since. Expansion stretched its wavelengths into microwaves, now only a few degrees above absolute zero. Invisible to our eyes, it forms a nearly uniform glow for instruments such as COB, WMAP, and Planck. Nearly uniform, but not perfectly. Within it are minute temperature differences, tiny variations in the density of the young universe. Gravity drew matter toward the denser regions. Over immense periods, those differences grew into filaments, clusters, and galaxies. The modern cosmos was written into the oldest visible light before the first star existed. The cosmic microwave background is therefore a boundary of vision. Ordinary light cannot show us an earlier scene because the earlier universe was opaque, but it is not the beginning itself. The Big Bang was not an explosion at one location inside emptiness. It describes an early state in which space everywhere was hotter and denser. The microwave background comes later, after hundreds of thousands of years had passed. Scientists may probe earlier periods indirectly. Neutrinos and primordial gravitational waves might preserve traces from a younger universe. Yet these messengers cannot perform the miracles sometimes promised of them. They cannot bring news from beyond our true causal horizon. No telescope, neutrino detector, or gravitational wave observatory can receive a signal that has never had time or will never have the opportunity to reach us. Technology can reveal fainter messages. It cannot repeal causality, and causality has more than one boundary. The most deceptive of them lies much closer than the edge of the observable universe. Part 3. Three horizons. The word horizon suggests something simple, a distant line separating what can be seen from what cannot. In cosmology, there are several such lines. They are related, but they do not mean the same thing. Confusing them can make the universe appear far stranger than it truly is. The particle horizon limits what has affected us up to the present. It gives the observable universe its radius of roughly 46 billion light-years. The second is often called the Hubble sphere. The farther a galaxy is from us, the more rapidly the intervening space expands. At roughly 14 billion light-years today, that separation grows at the speed of light. Beyond it, galaxies recede faster than light. This does not violate Einstein's speed limit. The galaxies are not locally racing past photons. Space between widely separated regions is expanding. Relativity limits how quickly one object can pass another nearby. It does not keep the distance across a changing universe fixed. Here comes the surprising part. The Hubble sphere is not the ultimate edge of visibility. We can observe faster receding galaxies. Their ancient photons began toward us under different conditions and later entered regions where they could make progress toward Earth. So, receding faster than light does not automatically mean invisible forever. For that, we need the third boundary, the cosmic event horizon. The event horizon asks a different question, not what can we see now, but which events occurring now could ever send a signal that reaches us even if we wait forever. With continued accelerated expansion, its present proper distance is on the order of 16 billion light-years. This produces one of the most unsettling situations in astronomy. Some visible galaxies are already beyond this event horizon. Their old light began toward us long ago, but light they emit today will never arrive. A message from Earth now will never reach them. We observe their past while excluded from their present. They are visible, but no longer reachable. Imagine a lighthouse across an ocean that stretches ever faster. The flash entering your eyes began before the current became overwhelming. New flashes leave, but the widening sea prevents their crossing. The lighthouse has not vanished. The relationship has. These distinctions change the meaning of the question, what lies beyond the edge? Beyond the Hubble sphere are objects we still see. Beyond the event horizon are events that cannot influence our future. Beyond the particle horizon are regions from which no signal has reached us. 3 boundaries, 3 different meanings of beyond. And because expansion is accelerating, the sky we inherited will not remain with us forever. The universe is slowly erasing its own portrait. Part 4. The galaxies that disappear. Look at a deep image from Hubble or the James Webb Space Telescope, and almost every fleck of light is a galaxy. Some appear as delicate spirals, others as red arcs, distorted by gravity. Many are so distant that we see them during the first chapters of galactic history. It feels like a permanent archive. It is not. The universe's expansion is accelerating. We call its unknown cause dark energy, one of physics' largest unsolved problems. If that acceleration continues in approximately the way our standard cosmological model describes, distant galaxies will become increasingly redshifted. Their light will be stretched to longer wavelengths. Each will appear dimmer and its visible evolution slower. From our perspective, their final images seem almost to freeze. Each new photon arrives after a longer interval and with less energy than the one before it, until the galaxy becomes not absent, but observationally unreachable. They will not blink out across a physical line. Their accessible images will fade, redden, and become harder to detect. Over roughly the next 100 billion years, galaxies beyond our gravitationally bound neighborhood will pass out of meaningful contact. The local group, the Milky Way, Andromeda, and dozens of smaller galaxies will remain held together by gravity even while the larger universe expands. Long before then, the Milky Way and Andromeda will have interacted, reshaping into a single, larger system. For observers in that remote future, the sky beyond this merged galactic home may appear almost empty. No grand field of receding galaxies, no obvious map of cosmic expansion. The microwave background will have been stretched to extraordinary wavelengths and may be effectively undetectable with ordinary methods. Future astronomers could still study stars and gravity, but some of today's clearest cosmological evidence would be hidden. They might reasonably conclude that their galaxy sits alone in an eternal darkness. They would be wrong, not because their instruments had failed, but because they had arrived too late. There is something profoundly unusual about our moment in cosmic history. We live late enough for generations of stars to have created the heavy elements needed for planets and life. Yet early enough for light from distant galaxies and the young universe still to reach us. The cosmos has given us a brief observational season, a window after the first stars, but before accelerated expansion removes the wider universe from view. Our maps are therefore not simply achievements of intelligence. They are records made during a fortunate interval, an age when the universe is still willing to show us much of its history. But even our largest map may be only a tiny patch of the whole. To discover what could lie outside it, we must first ask a more basic question. Does the universe itself have a shape? Part 5. Finite, infinite, or both. When people imagine the edge of the universe, they often picture a sphere floating in darkness. Inside the sphere, galaxies. Outside it, perhaps an empty void. But if the sphere represents the observable universe, the image is misleading. Its boundary is not where space ends. It is where our available information ends. Beyond it, the simplest expectation is more universe, more matter, more radiation, and more regions of space arranged broadly like those we observe here. How far this continuation extends is unknown. The universe may be infinite. If so, there is no outer wall and no final location. Travel would reveal more space, not forever in practice, because no traveler can overcome the cosmic horizons, but forever in the geometry itself. In a truly infinite cosmos, arrangements of matter might eventually repeat. There could be regions remarkably similar to ours at incomprehensible distances. This is a mathematical implication, not an observable discovery. We have no evidence of another identical Earth. The universe might instead be finite and still possess no edge. The surface of Earth offers a modest analogy. It has a finite area, yet a traveler can move across it without encountering a boundary. The surface curves back upon itself. Our universe has 3 spatial dimensions, but a positively curved cosmos could likewise be finite yet unbounded. Other topologies could also create finite space without an edge. In certain versions, a journey in one direction could return from another, though expansion and finite cosmic time might make it impossible. Measurements of the cosmic microwave background and other observations show that the large-scale geometry of the observable universe is very close to spatially flat. But flat does not automatically mean infinite. A tabletop appears flat, although Earth is curved. Likewise, a universe much larger than our visible region could curve too gently to measure. A flat universe could also have a finite topology. We can constrain the possibilities. We cannot yet choose between all of them. And this reveals a crucial distinction. The observable universe unquestionably has a horizon. The entire universe may have no edge at all. Asking what lies beyond the observable universe is scientifically meaningful. Asking what lies outside the entire universe may not be. If the universe includes all physical space, it need not sit inside a larger room. There may be no external direction, just as Earth's surface has no north of the North Pole. Yet our inability to see the whole does not mean we know nothing about it. The remarkable smoothness of the early universe offers a clue that our visible region may be a small part of something much greater. That clue leads back to a moment almost unimaginably close to the beginning. Part 6. The universe beyond our universe. Look in opposite directions across the cosmic microwave background, and you find regions separated by enormous distances. In a simple, early universe picture, some of those regions should not have had enough time to exchange light or heat before the background radiation was released. And yet, their temperatures are astonishingly similar. Why should places apparently unable to communicate look as though they once shared the same conditions? One leading explanation is cosmic inflation. Inflation proposes that extremely early in cosmic history, space expanded extraordinarily. A tiny region, once small enough to share similar conditions, stretched far beyond today's observable universe. Quantum variations enlarged with it, becoming the density differences from which galaxies developed. Inflation helps explain why the universe appears so smooth on great scales, why its observed geometry is close to flat, and where the seeds of cosmic structure may have come from. Inflation is a family of models, not a complete theory with every detail confirmed. Scientists still investigate what drove it and how its models can be distinguished. If some form of inflation occurred, it carries an astonishing implication. Our observable sphere may represent only a minuscule fraction of the space produced during that early expansion. Beyond our horizon may lie regions born from the same early cosmos, following the same broad physical laws, filled with galaxies whose light can never reach us. The observable universe contains everything photographed, every star named, and every world detected. Yet all of it may be comparable to one patch on a landscape extending far beyond sight. Some inflationary models go further. They suggest inflation ended locally while continuing elsewhere. Each isolated pocket could expand into a so-called bubble universe. This is one route to the multiverse. In different bubbles, the details of physics might vary. Particles could have different properties. Forces might possess different strengths. Many regions might be sterile. A few might permit long-lived stars, complex chemistry, or observers wondering whether anything exists beyond their sky. It is a powerful idea. It is also deeply speculative. No bubble universe has been observed. Searches for ancient collisions in the microwave background have produced no accepted detection. The multiverse should therefore not be presented as the answer. It is one possible consequence of certain models, an idea at the boundary where theoretical physics confronts the limits of testing. And it raises an uncomfortable question. If another universe can never send us information, in what sense can science distinguish its existence from its absence? The answer may depend on whether a theory that predicts it also makes unique, successful predictions inside the region we can observe. The territory beyond our horizon may be vast, but evidence must still arrive here. So after every equation and every limit, what can we honestly say is waiting on the other side? Part 7. What could actually be there? We have now reached the outer boundary of observation. What can we honestly say lies beyond it? The first possibility is the least dramatic and the most conservative. More universe. On very large scales, the cosmos has similar properties in different locations and directions. If that pattern continues, beyond our horizon are likely more galaxies, clusters, voids, and filaments. They need not be exact copies of those nearby. Local arrangements would differ, just as one forest differs from another while following the same ecology. But the underlying ingredients and physical laws may remain familiar. The second possibility concerns topology. space beyond our horizon, might connect back to our region. The universe could be finite without a boundary, its shape hidden because light has not traveled far enough to reveal repeated patterns. Astronomers have searched the microwave background for matching structures that might reveal such a cosmic wraparound. So far, no conclusive pattern has shown that the universe closes on a scale small enough for us to see. The third possibility is an extent so enormous, or truly infinite, that our visible sphere becomes cosmically insignificant. There would be no outer edge, only horizons belonging to different observers. And the fourth is the most speculative. Regions separated not merely by distance, but by inflationary history, perhaps forming other cosmic bubbles with properties unlike our own. These possibilities are not equally supported. More ordinary universe follows most directly from what we observe. Global curvature and topology remain open questions. A multiverse may emerge from some theories, but it has not been confirmed. That order matters. A compelling documentary can explore every possibility, but science must keep a clear boundary between the conclusions suggested by evidence and the idea that remains only mathematically possible. There is also a possibility people often imagine that science does not require absolute nothingness sitting outside the universe like darkness outside a room. Nothingness is not empty space. Empty space still has geometry, fields, and possible events. True, nothing would possess no distance, duration, or location. To ask what exists in such nothing already gives it properties it is not meant to have. The question may dissolve before it can be answered. Perhaps the deepest mistake is treating the universe as an object placed somewhere else. It may not have an outside. It may simply contain all the places that exist. But one final revelation remains. The boundary we have traveled toward was never located only in the distance. It has been surrounding us and moving with us the entire time. Return now to the night sky. The stars appear fixed against the darkness, but nothing about this view is still. Earth turns. The sun moves through the Milky Way. Light arrives from different moments in cosmic history, while expansion changes which events can ever reach us. And wherever we go, the horizon goes with us. If humanity settled another galaxy, our observable sphere would shift. New regions would enter view, others would leave. We would not escape the horizon, only change which one belonged to us. There is no single transparent shell fixed around a privileged Earth. There are overlapping spheres of possible knowledge around every observer, shaped by location, time, and cosmic expansion. The edge of the observable universe is therefore not the end of existence. It is the edge of a relationship. On one side are events able to reach us, to leave an image, alter an atom, bend a detector, or become part of a human thought. On the other are events with which no exchange is possible, not hidden by dust, not concealed by distance alone, separated by the structure of space-time itself. Way to study its own horizon. We may never cross that horizon. We may never receive a message from what lies beyond it. But standing here, during this brief age in which distant galaxies still fill the sky, we can recognize the boundary for what it is, not a wall where reality ends, not a curtain hiding a promised answer, but the farthest shore of everything that can ever reach us. Beyond it, the universe keeps its silence. And on this side, for a little while, we are here to listen. If this journey changed the way you see the night sky, share your theory below and subscribe for our next voyage beyond the known universe.